Hi there, my name is Rick Butts. I'm the creator of Edestol. In this video, I'm going to show you how to use motor control centers in the program. Let's get started. Okay, let's launch the program. And let's create a project. And we're going to put it in just the standard Edestol, and we're going to just call this project MCC. All right. And we got as we know, every project gets a source. I'm going to click on it. And we're going to call this MSG. So this is main switch gear. Existing. All right. It's not a service entrance. We're going to go, if it's got 480 volt, 3.4 wire. And so now we have a power source, and we're going to go to motor control centers. We're going to pick the motor control center. We're going to drag it there. Oh, that's right. Okay, so this is not a service entrance. This is an existing switch gear, represents an existing switch gear. And what it tells us is that you can't insert an MCC on a source unless it's a service entrance. So what we got to do, we got to go over here to protective devices, and we're going to add a circuit breaker to that existing switch gear. All right, it's going to say a new branch, and we're going to say just CB08. Okay, and this is a new MCC. We're going to call this MCC2, and we don't really know how big it's going to be, so let's just make it 400 amps for now. And if you want, obviously, if you've got attributes, if you've got a special type of circuit breaker, type, let's just say power circuit breaker, trip unit, we're just going to go fixed thermal, adjustable instantaneous, and we don't have any options or anything else, so that will go with that. So here's our breaker in our existing switch gear. Then we're going to, now we had no cable for that one, didn't create a cable because that circuit breaker is part of that switch gear. So we're now going to insert a motor control center on that breaker. And it says bus size 400 because you have 400 amp breaker. We're going to call this MCC2 for process line 2 MCC. And since there's an upstream breaker, a protective device, your main device can be main lugs. If you want, you can put a molded case switch in there. See, it sizes it for you for 400 amps. If you have special attributes around your main device, you can click on main device attributes. We don't have any attributes for molded case switches installed in here. But if we decided, you know what, it's a long way. It's a long way from that main switch gear. So let's put a main circuit breaker in it. There you go, you're fixed. And then you can go back to so this is circuit breaker options, trip unit, whatever. Maybe you want ground fault or something like that. So let's put just LSIG on that. So that's that breaker itself. And you see you don't have any connected amps. You don't have any minimum circuit size because there's no connected amps. The circuit design size, this circuit design size is your final circuit size. And this is what the cables that feed the MCC are based on. Minimum circuit size, once you start adding motors, you'll see that this is the calculated value of what the minimum requirement is. But since this is the motor control center, we are going to size it based on the main device trip, the service cables. So we're going to press OK. And here's our list of cables. And we're going to go with Houston Wire and Cable, and we're going to run THHN, THWN, single conductor, copper, in a raceway. If you wanted to run a cable tray and you had one specified, you could select it here. We're just going to say that the cable just runs within the electrical equipment room, and it's air conditioned, so we're going to leave it at 86F. And since it's within the electrical equipment room, let's go with an EMT. Okay, so you've got your cables specified here, your sizes, and now it's sized based on 40%. which is so you end up with a 3-inch EMT, and you have a fill of 33.4%. So here's all your different cable requirements you see up here. The uncorrected size using the 75C cable is 600 degrees, but we basically down here said it's 90C wire was the cable we're using. So the corrected and adjusted size uses the 90C cable. It would, using just simply 90C, would come up with a 500 MCM cable. So basically it's the larger of these two. So we end up with a 600 KC Mills cable for a feeder, and it's one parallel run. So we're going to go with that. So what you see is now it has automatically created the cable for you. It is a P cable, because if you look at cables up here, P cables are 241 through 2000 volts. So it is a P cable, and the designation for the P cable, as you know, is the device that cable feeds, MCC2. Now let's go ahead. So we have an MCC up here in powers. We don't need to look at cables anymore. Let us, now we're going to just add a motor. Loads, let's just say motor, and let's say we're just going to say M1, and that is the process line to crusher. And let's give it a sizable, it's 250 horsepower. Okay, and we're going to run a cable, so we leave that the way it is. It's not a spare. Here you can see that the circuit minimum size, the connected amps, is the full load amp. 302 is connected amp. So this is the cable that feeds, this is the sizing information that feeds this motor. And basically it is, this is 125% of this value for connected, which is the connected is the full load amps. If let's just bump over here, make this a KW, you'll see now, since this value of 250 horsepower is no longer in the code book as a horsepower size, we are calculating it based on the power factor and efficiency and nameplate voltage. If you go back to horsepower, this value is actually listed in the code. So we are taking the table value for the full load amps. Full load amps becomes a connected amps. Connected amps times 125% gives you your circuit minimum size. Our circuit design size, which is the field that actually is used to size the cables, uses as you can see, the minimum size for this cable. If you had information on the motor you wanted to click on, I'm not sure we've got attributes selected. Oh yeah, okay, so there's your enclosure. It could be a totally enclosed fan cooled. Let's see, and your synchronous speed, let's go, maybe it's a 1800 RPM. Classification, this one is not, so we're just going to leave it there. So there's your actual some attributes. If you had a manufacturer and part number and you wanted to assign it here, you could. Let's just go ahead and say ball door, and we're going to create these, and ball door, and so there's our manufacturer and part number. So now let's go ahead and insert this on that MCC, and you get your cable. You get your cable requirement. In this case, you can see it's an ABC connection. The size is the circuit final size there on the motor cable, and it is 377.5. In this case, this motor is going out into the field. It's not air conditioned, so we're going to put 104 is the sizing requirements. We're going to stay with single conductors, and there you go. We're going to stay with HWC. To help you, the last time you created a device in power cables with a P cable, it saves the last cables and the settings that you had so that you don't have to go through it again. If you go back and forth for different types of cables, maybe you want multi or single, you'll have to make some adjustments. but there you go. So we basically, in this case, it's 500 using the 75C and then 500 using the 90C, so 500 is the cable size. And in this case, this is the actual cable that connects to the motor itself. So you have to remember, when the design is going to be complete, the cable that connects to the motor will actually go from the disconnect. We're going to put disconnects in, and it goes from the disconnect to the motor itself. So in this case, we're going to specify a liquid tight flexible metallic conduit, and we're going to leave that there. So we'll stay with 3-inch, but it turns out to be a 29.2% fill. The ground cable is actually the same specs as so HWC, THHN, THWN is the ground cable specs. If it turns out maybe you wanted bare cable rather than an insulated conductor for a ground, just click on ground. And let's go up here and select bare, and you can either do your standard Chapter 9, Table 8 bare stranded, or HWC also makes a bare stranded cable, so let's go with that. So there you go. So now you've got your two HW001. These are your part numbers for these single conductors. You need 3. And you got one HW000, and it's a number 2 is your part number for your bare cable. So you get a little slightly different fill because the ground cable is a little bit smaller, but same basic idea. So let's just save that. And now we have an additional cable created so we have a cable running to the motor, M1, and we have a cable going to the MCC. Click on down here. You can look at these cables using your cable schedule. This is kind of just your cable schedule. It tells you, but let's look at, these are all single. Let's look at cable raceways, cable dimensions. You got different things you can look at for your different cables. There's your specs on your actual sizes. There's your cable raceways. We have not created any raceways, but you can see P cable M1 runs from MCC2 to M1. P cable MCC2 runs from runs from MSG circuit breaker 08 to MCC2. That's that cable, and we haven't. We'll assign these conduits here in just a second. We'll actually got to create these. So back up here to Motor Control Center. Here's kind of a thing about Motor Control Centers that's unique in this program, and that is that you can, obviously a Motor Control Center needs a starter to operate this motor, but we needed a way to add motors without knowing what the starters are. Typically you have a motor list, but you don't know whether they're adjustable speed or whether they're fixed or whether you need a reduced voltage starter. So motor control centers, motors can be inserted directly on motor control centers without a starter. If you were to go from a circuit breaker, you couldn't put a motor right on a circuit breaker. You would have to have a starter on the circuit breaker, then you can put the motor on the starter. So MCC is unique in that way. If you do like a motor control, you also can do a motor control panel. We'll get to that in another video, but you cannot you cannot just drop a motor on a motor control panel. You have to put in your power distribution blocks. You have to put in your different protection devices, your starters, or your adjustable speed drives, whichever you need. So you can't do that. But motor control centers, you can. Primary reason for that is, as I said, you need to know, you'll have a list of motors, but you won't know. So you can just drop your motors in and calculate your rough service size. But also we have the ability to import lists of motors, and that's over here. We'll get into this into another video, but you can, if you have 20 motors, you can list them in a spreadsheet, We've created a base import spreadsheet for you. You can list all your motors, your horsepowers, and your horsepower versus your units, whether they're kWs or horsepowers. And then you can import all of those motors into a particular MCC. So I just kind of wanted to clear that up a little bit. You can't do that in most cases, in almost all cases, except for this. You have to have a control device. If you drop say a heater on an MCC, it wouldn't work. You have to put a heater control device in first and then drop your heater on it. Motor control centers, you can drop motors. So let's get another motor here down to loads. And we're going to add an M2 and we're going to call this a bucket elevator. And make it a 75 horsepower. Same deal. We're going to run, you got your connected, you got your FLA for the table value, and we're going to create a cable when we press this. So now you get the same old idea. If you want your ground to be different, but we'll just stay with insulated ground here. Still, it kept your liquid type flexible metallic conduit from the last insertion you made. In this case, we're going with number 1s, number 6 ground, and there's your Houston wire and cable part numbers there. So press save. And now you can see what happens here. So we put a 400 amp MCC in, but we didn't really know what size it was going to be. So you get this warning that something is wrong with these. So let's keep going. It doesn't hurt anything. It just kind of is there for an indicator. So let's put our third motor in, and we're going to add that, and we're going to say M3, and this is a conveyor, and we're going to call this 50 horse. Okay, same deal. Attributes, let's go to part numbers. Balder, you can now list because it's already created. If it happens to be a different one or close to it, 777. So it has a different one. Let's go to attributes. Synchronous speed, 1800, enclosure, TEFC. There you go. And so now we're going to create a cable, same deal for M3. And you kind of can get pretty quickly, except in this case, your liquid type metallic conduit's 1 inch. There you go, same specs. And so now basically you have your third motor. Well, you go and you look at your MCC, what's going on here. And that is, you can either look at it here. You can see now your final circuit size is 400. That's how we sized it. So we got cables feeding this thing, 400 amp. But you can see that our connected amp is now, with all those motors, you have jumped to 463 connected kVA, and then your circuit minimum size is 463. As you know, it's the sum of the motor connected amps or full load amps plus 25% of the largest. So there you go. You have another type of report. If you want to actually look at the circuit calcs, you can basically see what's going on. You have a connected amp, which is the sum of these. You have a circuit minimum size, which we calculate. So for each one, 65 circuit minimum size. For each motor, circuit minimum size is 25% added to the connected amp, or FLA. In this case, FLA and connected amp are both the same. You basically you sum all your motors, which is circuit sum all motor amps. So there's all your FLA summed together. And then which is the largest motor, so it takes 25% of that, adds it to all motors, and that gives you your minimum size. Unfortunately, for MCC2, our final circuit size is 400. So the warning is that our minimum size is larger than our final size. So we get a warning. However, in this case, if you look at it, we've got a main device. We have to bump up. So let's just make it an 800. But your bus size has to be larger than your trip unit, your circuit breaker size. Actually, let's just go back to main breakers, main lugs. And your bus size has to be larger, so you can increase that. But basically, now, rather than the main device size, it's actually the upstream overcurrent. OCPD stands for overcurrent protective device. So it's the upstream breaker that is sizing this. It's not the bus size, because you can have a larger bus size with a smaller upstream breaker. So there you go. So basically that did not fix the problem. The problem is that this circuit breaker is too small. So basically when you connect it on it, it is the circuit breaker then came up and said, oh, it's too small. So it's going to resize it to you. It says it's got to be a minimum of 600, but we're going to go to 800 this time. So now we've got that. And then basically it automatically, when you adjust the overcurrent protective device size, the downstream is immediately launched, because you generally affects the downstream device, and it says, oh, you put a 600 in. 600. We actually are going with 800 here. Did we make that circuit breaker 800, or do we make that circuit breaker 600? And it adjusts your feeders that are going to the breaker, and now you have two parallel runs. So basically these are the cables that we were using. We're using EMT. It's now increased that size from 400 to 800, and it's increased the parallel runs to 2. So everything else stays the same. However, when you get done with that, you go down to cables. Now you have two cables feeding the MCC. One is parallel run A, one is parallel run B. Now let's look at, we're going to look at the whole system from power. And let's go up and look at our general, just so we can get our sizes here. So basically we put an 800 amp breaker in there. Okay, so there's your 800 amp breaker feeding MSG. Actually, it's an 800 amp bus. ID tag circuit breaker, and then it's 800 amp circuit breaker, and then an 800 amp bus. So there you go. This is kind of your whole thing. So now our circuit final size for main switchgear, really it basically says this is your service over here. So this is the final size, which for a source, the final size equals the minimum size. But for your breaker itself, it is 800 amps. Your MCC is 800 amps, and each of your motors are their respective FLA times 1.25. So now you have that. It sums up, so you can basically say, here's what you're adding to your existing MCC. Do your calculations on add your existing load, and now you've got your MCC, your motors connected there. So what are we going to do? Let's just try the next step would obviously be, we're going to put a reduced voltage starter on M1, because that's our extruder, or I believe it's crusher. So let's do a reduced voltage starter M1. And it says that basically, if you have a motor connected downstream, it'll say, okay, you need a reduced voltage starter at least large enough to feed the motor. So there you go. Here is it doesn't have, I'm getting this corrected. This should be this connected value down here. You will get a 0 if you just connect a starter or an ASD just directly to an MCC with downstream motor. But we've got now we do have a downstream motor, so we've got to transfer this number up here. This is kind of in process. Hopefully by the time you see this video, this will be corrected. But it tells you which size you need. And now the idea is that this reduced voltage starter is part of the MCC. So it says part of MCC2, and you don't need a cable, because that is a bus connection from the reduced voltage starter to MCC2. So when you say, okay, there's your reduced voltage starter, but it does not create a cable, because there is no cable connection that we have to be concerned with. There you go. So there's your reduced voltage starter. We can also do adjustable speed drive. So let's feed the conveyor with an adjustable speed drive. And in this case, There's your downstream bucket elevator, 96 amps. We have several different, this information on these particular drives is contained in user data, and I'll do another video that shows you the details of this, but you can actually select the supplier of the drive that you want to use. Let's use Schneider, and I believe all we have is ATV 630 style installed. And what it will do is it will look at the output of the drive, and it will make sure that that output, it will get you the smallest drive, select the smallest drive that meets the motor conditions, and the output of the drive is at least as much as the connected amps for the motor. So it has selected, and there's your part number for your drive, your efficiencies, frame size, loss that you have. And then for this, the connected amps, there you can see the connected amps works. In this case, we got 96. You have the connected amp comes directly from the motor regardless of the drive itself. However, if you look at the input rating of the drive, 84.2 there, it is actually the final circuit size is basically, in this case, this is an equal sign. We need changes to minimum size, make it a little bit easier to read. But the minimum size, the circuit minimum size feeding this ASD is the input rating times 1.25. So that's how you get to 105.3. So even though you have a connected amp of 96, your input rating for the feeder that actually goes to this drive is based on the input rating of the drive. It is not based on the connected amps of the motor. So basically the circuit minimum size is the final size. This is what, if we were running this to a standalone drive from a circuit breaker directly and we actually had to create a cable, this is the size that we would use. 105, which is 125% of the input rating of the drive. But in this case, it's connected to a motor control center. So it is part of a motor control center. So that is a bus connection that's made by the manufacturer, and we're not concerned about that connection. So we basically have it automatically check no cable for you. We do not size the main device circuit breaker. We just say, yep, we do want a main device and we're going to have a circuit breaker. You could also use a fuse disconnect switch if you wanted. This is more for printing out in our detailed reports. When you go to a motor control center manufacturer and you do a drive, you don't have to size it for them. They will size the fuses or they will size the circuit breaker for you. So basically, we just tell them, do we want a main device? If you were to have this ASD fed directly from a circuit breaker, you could actually drop this ASD right on another circuit breaker for MSG. And in that case, if you dropped an ASD on it, you would have an option here. Since you had an upstream protective device already, you would have main lug here, or line terminals, I think is what it's called. So you don't always have to, you do have the capability of installing just a standalone drive with no upstream protective device. So there you go. We're going to say okay. And now you have M2 fed from ASD. All right. And so there's your reduced voltage solid state starter. You also have ASDs. And now for this last 50 horse, we're just going to put a full voltage starter on it. And let's try another. You can drop it right on the motor. Let's try. This is, now you see this new branch or existing branch. So basically, are you wanting to install, if you see this thing, this basically means you have the capability of putting a drive, or excuse me, this is a full voltage starter right on this motor. Right on this motor control center. Or you could say, no, we have an existing branch. We want to put it on that branch. And in this case, we have an existing branch. And the only thing that meets the requirements is M3. So basically, we're saying, yes, we're dropping a full voltage starter on MCC2, and we want it to be feed M3. If you had other motors that didn't already have starting devices on there, you would get these listed as well. So you could do it this way, or you could drop in this case, you could drop that starter right on M3 and it knows, okay, you want a starter for it. Oh, I must have picked a reduced voltage. So let's just cancel out of that. Let's go down here and say full voltage. All right. In this case, we'll just drop it right on the motor. It means the same thing. It becomes part of MCC2. It automatically fills in what the description is, calculates all these things. And in this case, it's going to be a full voltage. Let's say we want to run it both directions. We're going to make a full voltage reversing NEMA starter. You could use IEC, whatever you want. And it gives you your full load amps, and away you go. No cable for this one because it's a part of the MCC. So now you have an MCC that is basically completely fitted out for these three motors. But we also want, and we can see what our actual minimum size connected amps total. If you just sum all the motors, you get 463. In this case, let's go back. We're going to look at circuit calcs. In this case, one of those motors is an adjustable speed drive. So in this case, the circuit calculations they're the same. They're always calculated the same way, but we're going to use more fields because they have values. In this case, you have basically connected amps. You have circuit sum of all motors. So there's all the FLA values. Here's the sum of the input amps of the motor. So these are the drive ratings of the motors. Here's the motor FLA values of the motors, but these two fields are motors that are on drives. So there's the input rating of the drive. There is the FLA of the motor that's on that drive. And here is your largest motor that's not largest full voltage motor. It's basically the largest motor that's not on a drive. So what it does is it picks the largest of either the input rating of the drive for that motor or the full voltage FLA. So it basically is replacing the largest, rather than just saying the largest full voltage motor. It's basically if your largest motor is on a drive, it would then take the full voltage, the input rating of the drive as the largest motor and multiply that times 0.25. So basically what you get is connected amps, which is everything, plus, you get connected amps. If you had other continuous, non-continuous loads here, you'd have larger value. But basically it subtracts out this value, takes this value, subtracts out the FLA values of your ASD motors, adds in the input ratings of your drives, takes the largest times that of times 25%. If you have continuous loads that are three-phase, you get 25% of that. If you had continuous loads that are single phase, it takes 25% of that, and it will give you the largest value. So we'll go ahead and add some of those here in a minute, but there you can see how that works. If you've got any questions on this, we may get into this a little bit more detail in future videos, but this is your standard calculation for minimum circuit size for an electrical system within this program. This is the kind of the heart of the system from a calculation standpoint. Now, what we've also got here is let's go ahead and just add, so you can see what a continuous load here looks like. Let's add a heater control in here, and let's put that onto motor control center. It's going to be a new branch, and this is just going to be an SCR controller, and it's going to be a fuse. So let's just say heater control device zone 1A. All right, and this is a process. All right, and we'll just set this at, say, 30 amps or so. Okay, so there's no connected amps there now. All right, and fuse, this may be, we've been working on this, so let me see what, I'm gonna put it at 30 amp fast. There's your fuse disconnect for your motor, for your heater controller, and your SCR controller size. So let's press that on there, and then we're going to go ahead and add a heater to that. Down to loads, and let's put a heater, and let's just say zone 1A per. And let's just say it's going to be a 15 kVA. Actually, let's make that kW. Okay, so there you get your circuit design size. Away you go, and we're going to create, in this case, this is running from the heater controller in the MCC out to the actual same concept of sizing your cables, the whole thing, except in this case, since this is not a motor and it's it's under 100 amps, it uses the 60C to size your uncorrected size there. So you get number 10. So if you went with 90C for your corrected size, you could use number 14s, but we're going to use the uncorrected size. It's larger, so there you go. You get 3 number 10s, and away you go. So there's your cable you can see you've created your cable for your, so now you see what happens over here on calculations. Okay, let's click back up here and say now, in the case you now have 18 amps connected to 3-phase. So that was a balanced 3-phase load. So now to do your circuit minimum size, you're adding, obviously this value is already part of connected amps. It used to be 63 and now it's, 81. So you can see how that changes. So this basically fills in. So this is all your different types of loads. If you have non-continuous loads, it doesn't show up on this report. There's ways you can see it. If you want to see connected kVA, you got your non-continuous fields over here. But looking at your circuit calculations, all your non-continuous loads are already included. Everything is included in connected amps. So really these fields right here are just your adjustments. So you got connected amps, which includes your 3-phase motors. It includes your drive or input ratings. It just includes your motors. It includes your non-continuous, your continuous loads. Then basically you're subtracting out FLA values that have motor and that are on drives. You're adding 25% of your largest either drive or full voltage motor. You're adding 25% of your continuous amps, and you're adding 25% of your single phase continuous amps. So that's how this works. You can actually, let me show you a little bit. You can kind of export this if you want to work out these in a spreadsheet. You can actually export to Excel, call this whatever you want. You're going to have to do some manipulation. It comes out, I believe, as text. You're going to have to create and turn them all into number fields. But then you can do sums to check this, and you can do some testing or calculations on your own to see just exactly how this works. Even though all these circuits, this adds up, your circuit minimum size is 549. Your final circuit size is based on your upstream protective device. That's an 800 amp breaker, so you're good to go here. Okay, so there you go. So now let's do the next thing is now each one of these motors, we have chosen to put disconnect switches on these. So let's just go down here to switch device, and you go disconnect switch, and we're going to click it on M1, drop it on M1, and it knows that you want one. So basically this is not part of anything. This is an independent. Let me see if we got attributes available. Yep, so you want to, let's just go outdoor NEMA 4, listing, UL listing, accessories. We want one aux contact for status information. Okay, so there's our disconnects. And it needs, since it's final circuit size, this switch size is not based on final circuit size, which is 25% more than the connected amps. The switch size minimum is actually based on 15% additional to the connected amp per the I believe it's 430 in there for your disconnect sizing. I should probably list 15% down here. Right now we're not doing that. So basically it says of the sizes you've got available, you need at least 400 amps, or at least it's actually 15%, whatever that number is. So 400 amp works. And we're going to do a cable here, but in this case, so now we're going to kind of look at what happens. In this case, we know this is the cable that runs from the starter to the disconnect. And in this case, we are going to run it through a cable tray. So we are going to run multi-conductor cable, and we're going to do, there you can see cable type is TC exposed routing. Turns out HWC makes one, so there you go. So in this case, rather than 3 single conductors and a ground, you have 1 cable. And your ground specs, you can't do ground specs because it's included in the cable here. Now in this case, we're going to do conduits in the field. They're going to be RMC. And let's also bump the process temperature, the ambient temperature for the cable itself up to 104, just for all our D rating. We still stay with 500 KC mils, but you know what, 500, I don't really want to run 500s to that motor, so let's run 2 3/0. Okay, so just click your parallel runs up to 2, and now it's still single conductor per parallel run, single cable per parallel run. But you'll notice in RMC now, since you only have 1 cable, you can do a fill limit of 53, but and it's still 46, so I'm thinking 46% fill out in the field for a single conductor cable. Let's go 40% fill. So now you're down to 32 because you're pulling a single conductor, so we're going to bump it up to 2.5. Now this doesn't actually create a raceway. This kind of just sets up your specs. If you need a quick and dirty number, what size do I need for these cables? There you go. I'll show you how this is used here in just a minute. Okay. So that's disconnect for M1. Now in this case, so you can go up here and you can say switch devices and you can drag another disconnect. But we've already selected attributes for this disconnect, and I don't want to have to redo that over and over. So what I'm going to do is right click, and I'm going to say copy device, and I'm going to go down here, and this is just like dragging a device to this point, except this case you need a 200 size, and it does all the sizing, and it'll do cables when we do that, except, see, you don't have to select your attributes. It copies all that stuff. If you had a manufacturer part number, it would copy that as well, so you would want to adjust that since it's a different size. But it kind of saves you a little bit of work by doing copy paste rather than dragging it in. So let's do that. Created a cable. Here's our cable, same specs as last time around, and we're still using the same percent fill size limit. We could go down to 53 because that's our, if we wanted to, but we're saying, let's go with 40% fill for these single cables, and let's do that. And then there's your branch. We're going to copy that. We're going to go down to M3. And you get 100 amp on this on M3, and we're going to create that cable. Now let's see what we've got here. All right, so basically you can now look at your cables. Click on, let's just do all the cables, and what you've got now is you have this is a raceway report that we've already shown you. You can actually, this is all the different fields available in the cables data table. I put them here kind of more for testing, and as we need different what the reports are is just selections of, here's just fields 1 through 24. You can see them all. There's all sorts of different fields in here. There's cable amps, there's size reference, there's conductor cover, means different things. So every field, and then basically I've picked out what we need for what you would consider just a generic cable schedule. So these report configurations are contained within user data, and you can change them, add to them, modify them any way you want. You can delete them. So you can look at the data within your cable schedules in any way, and you can create a new report, have access to it right here. But I've created these three right now, so let's look at raceways. So basically, we started out running from MCC to these M1s, and here's your M1 cables. They, rather than running from the MCC, now they run from the disconnect. It's P cable, still P cable M1, but now the from is the disconnect rather than M1. When we added the disconnects, you now have a cable going to the disconnects, but rather than running from the MCC to the disconnects, they run from the RVST. Or from the starter device. This is kind of the convention that we use. If something is part of, you have the parent device, if you will, dot child device that goes on there. So that's the convention that we use. And you could, if I were to add, let's just say something else onto RVST and made it part of RVST, it would be MCC2.RVST M1 dot whatever additional part of. So you can kind of do that. And this is all, this part of stuff is all for reporting that I'll show you in a minute. And then you've got your parallel conductors going from your circuit breaker and your main switchgear to MCC2. Started out with one cable, but we upsized it so it automatically made two parallel runs. We also decided M1 up here was one. You could get away with 1/500, but be easier to pull and lay it in the tray if you divided it into two. So there you go. We've created two parallel runs. And then we have one cable going out to our heaters from our heater control device, which is contained within MCC2. So that's that. I think that's enough for now. I want to show you a little bit. You have these report utilities, detailed reports, and you can basically, these are all, so you can do power devices and control devices, but really go ahead and click on MCC here. And what we're going to do is you could select them all if you wanted a detailed report on everything, but we're going to unselect. These are all the devices that are available. And I wanted to show you what this part of works, how this part of works out, because we're going to go ahead and we're going to run a detailed report on MCC, okay? If we had more than one MCC in the job, it would do them all, but we only happen to have one in this case, and it's run the report, okay? So we're going to go to where it dumped that report, and we're going to look at documents here. And Edestol, and then this is our subdirectories for our generic documents. Edestol project is in here. Libraries, this is where as you know, this is where your user data, sysdata is all the sizing information from the code book. User data is stuff that you can adjust, and report configurations. This is where we put the drives. You've seen that. And let's go to reports. And there's the MCC that we created. It's the device type MCC. The label, we just called it MCC, and it printed it, just printed it. So let's look at this. So what you have here is you have MCC device type, project, we call the project MCC, device type MCC, and we tag the MCC, MCC2. So there's your specs on the MCC, and then there's the specs on the main lug only device. There's not much to that, so you get one line, it's part of. Now the next line is, okay, you have a reverse voltage starter that's 3-phase, 250 horsepower. You've got a ASD, and the main device on the reverse RVST, the reduced voltage starter, is a circuit breaker. You've got ASD, MCC2 ASD. It's the size. It gives you all the specs here. It looks to me like we got a little cleanup on spacing and make this look a little bit easier to read. But there's the idea. Something I'm seeing here that we may not have selected any attributes. The attributes would be listed here as well. So this is the idea of what you've got. So basically you have this report. It comes out in a text report. If you want to open it up in Word or something, you could format it a little bit easier, but it kind of gives you a straight text dump of what that is. And you could actually use this as some sort of a bid device, bid document. Let's go back to reports, reports, detailed reports. Let's just click disconnect switches, run reports. That did have, and go back to the report, and it just created, okay, so that's project MCC disconnect reports. There you go, and so in this case, for each disconnect, you've got to disconnect DSM1, 600, 400 amps. So it gives you basically the device, the documentation you need to, once you've created your project, you've specified things in attributes, it's sized everything your project, and now you can just create quick reports of what the project consists of, the devices that you need to go out and get quotes on. And you can use that for this purpose. You can also, let's go up here. I want to show you something else. I'm not sure whether I've showed you this before, but I've got, let's just say you just want to look at the information. You just want to look at motors and MCC. I put this up. Sometimes this can be very confusing when you get all these different things. It doesn't necessarily mean these just sum together. There's lots of calculations that are occurring throughout the project. So let's just go back to our base general. And you know what? I only want to look at, this is all the devices you have available. And I just want to look at the MCC. And I want to look at, let's just say motors. Let's just say motors and heaters, just the loads on the MCC. There you go. So there's your, and you can print this out. You can either print direct or you can export it to a Excel spreadsheet. So you have a whole, I've tried to give you ways to easily get access to the information and use it. You've got all these different other, there's all your connected amps. You want to look at the different phases. This would be for single, if you were looking at single phase types things. So this is kind of the ways. Another little thing I've got here is if you've clicked a motor control center, rather than all let's just say you want to select all, but you really just want to display the items that are immediately connected to that MCC. So this basically says list immediate connections only. So it's just kind of another way of manipulating your screen so that you're not looking at so much data all the time. So this is enough for now. I'm sure it's already gone. I'm not even sure what the time is, but that's enough for now. I'll be doing some more videos on more stuff. Have a good day. Thanks. Bye.